welcome back to our machine design series. Today we're continuing our discussion of spur gears by talking a little bit more about the gear tooth profiles on a spur gear, or really any gear. Now, gear tooth profiles are almost exclusively all the same type of shape, and we call that shape the involute of a circle. All right, and what that means is if I were to take a small cylinder, let's imagine this is a cylinder, we're looking top down on it, and now I've got a string wrapped around it, let's say. I've got this string that's wrapped all around, and I'm gonna start unwinding that string. So maybe I take the end from somewhere over here, and I start unwinding. At first I pull it straight out, right? And then as I continue unwinding, I'm following this path. It's getting wider and wider. So at any given moment, at the beginning, my string was right here. As I move along, my string is here, here, here. You get the picture. And that path that our string is tracing is the involute of a circle. All right, and if you've noticed on a typical gear tooth, let's take a look at this drawing we have up here. All right, so if we look at this shape of a gear tooth, you'll notice that this baseline shape, it does resemble the base of this shape of the involute curve, and that's exactly what it is. So that's the shape of a gear tooth. Now, as it's rotating, the curved surface of this gear tooth is going to press against the curved surface of another gear tooth. So if I were to draw maybe the mating gear up here. All right, here's our mating gear tooth. And when these two gears press together, these two curved surfaces press together, there is a point of contact between the two, and at that point of contact, these two surfaces are tangent to each other, right? These two surfaces are tangent, and we can draw our contact force, which is going to be normal to that surface. So the blue gear tooth here is exerting a normal force on the green gear tooth, and the green gear tooth is exerting an equal and opposite normal force on the blue gear tooth, assuming that we don't have any acceleration. All right, now let's take another look at our pitch circles for the two types of, our pitch circles for two gears that are enmeshed together. All right, so looking at these two gears that are in mesh, we can first of all define a line of action that the contact force is acting along. So notice that in the drawing above, where we have this contact force, that contact force is not exactly horizontal, so it's not exactly following the pitch velocity of the two gears at this point. It's at this inclined angle, and that angle is called the pressure angle. It's the angle of the line of action for the gear teeth that are in contact with each other. and that line of action is also going to be tangent to the base circles of the pinion and of the gear. So if I can draw where this line of action would be, it's going to intersect the pitch point, so that's the point at which the two pitch circles are tangent to one another, and then it is going to also be tangent to the base circle of each of the gears, or the pinion and the gear. So something like that. That white line is our line of action. All right, now we've already mentioned the pressure angle, but let's show where it actually exists on our drawing here. So if I draw a straight line that is tangent to both of the pitch circles, goes through the pitch point, then our pressure angle is this angle here that is between the line of action and the direction of the pitch line velocity. So this is the direction of the pitch line velocity here. And there is our phi, our pressure angle. Now there's some standard values for the pressure angle for most gears that are in use in industry today. Okay, so the standard values today are 20 degrees, 22.5 degrees, or 25 degrees. I mostly see 20 degrees. The old standard was 14.5 degrees. So if you're working with an older system, parts that were originally designed, I don't know the exact date where it flipped over, but I want to say it was somewhere around the 1970s. So if you're working in an older system that was designed prior to the 1970s, or parts were sourced prior to then, you might have gears with a pressure angle of 14.5 degrees rather than the current standard. The pressure angle also helps us relate the radius of the base circle to the radius of the pitch circle with a fairly simple equation. It is r of the base circle, and I'll do a subscript I to indicate that it could be 1 or 2, is equal to ri, again that's 1 or 2, cosine phi, the pressure angle. And I'll write over here that I could be 1 or 2 for either gear 1 or gear 2. Alright, so that's all I have for you for this video. I hope you found it helpful learning about the shapes of gear teeth and how they provide equal and opposite contact forces between the gear teeth, where the line of action of the forces between those two gear teeth is located, and then lastly the pressure angle, which I forgot to highlight. And if you found this video helpful, I really appreciate all the likes and subscribes. That helps me continue making more content for free for you guys. In the next one, we will plan to talk about mesh considerations, so talking about the contact ratio, how many teeth are actually in contact with one another at any given time. We'll also discuss things like backlash and interference. So I hope you're looking forward to that, and I will see you there.